Hi again. In this video, we are going to continue to work out problems deciding whether a molecule is aromatic, anti-aromatic, or non-aromatic. In the previous video, we had seen examples that are neutral. We've seen examples that have large rings and small rings. We also saw examples where we have cations and anions. In this video, we're going to focus on molecules that have what's called a heteroatom. That's an atom that's neither carbon nor hydrogen. So if we have a sulfur, a nitrogen, an oxygen on the ring, that's called a hetero ring or a heterocyclic, right? Because it has a heteroatom. And then towards the end, I'll show you one pretty neat example of aromaticity in a molecule called calicine. But what about our first molecule that has a heteroatom within the ring? That's going to be, it's called furan. F-U-R-A-N. If your professor doesn't draw the lone pairs, okay, it is your responsibility to draw the lone pairs, because what's so important about aromaticity is for us to be able to count the pi electrons. And in the previous video, we saw that even a lone pair could be considered a pi electron if it is located in a p orbital. Now, I know that students get a little bit worried when they have to decide or even identifying, when do I choose for a molecule to be an atom to be sp2 or sp3? Okay. When you have an atom in the ring and it has lone pairs, okay, and it's singly bonded, then that atom can assume an sp2 hybridization or an sp3 hybridization. You know that when we were doing resonance, by definition, that lone pair has to be in a p orbital to participate in resonance, to be shared with the other p orbitals. So that means that atom has to be sp2 hybridized. Okay, but what about this oxygen? This oxygen has 4 areas of electron density. So normally you would think this is sp3. And it could still be sp3. It just depends whether it's beneficial for it to be sp2 or not. So what's the strategy? The strategy is, let us try to see if this is aromatic. Is it possibly aromatic? Okay. Well, for it to be aromatic, that means all the atoms have to be sp2, all the atoms of the ring. So we are going to choose, let's suppose, the oxygen is sp2 hybridized. Well, when we look at our rules, I think the first rule was, are all the atoms in the ring sp2 hybridized? So for rule number 1, sp2, all the atoms of the ring are sp2 hybridized, we're going to put a check mark, right? These carbons are sp2, that oxygen, we're going to pretend it's sp2 for now, okay? What about rule number 2? Rule number 2 was, is the molecule flat? Well, the molecule only has 5 atoms in the ring, and we had a cutoff saying that any ring molecule that has 5 atoms, it's too small to sufficiently get bent out of shape to become non-flat. So we are going to say affirmative, that molecule is flat. Number 3 is the hard part, because for this to visualize resonance, for this to have resonance, you could draw resonance, okay? Well, for that to actually happen, one of these lone pairs has to be in a p orbital, or else how can you make a pi bond if one of the lone pairs was not in a p orbital? How could those electrons be delocalized with the other p orbitals if that oxygen itself did not have a p orbital? Now here's the analysis though. How many lone pairs are in the p orbital? Do we count those as pi electrons when we figure out if it follows Huckel's rule? So these are questions that we'll need to answer. Well, let me show you a picture that will help you believe that this molecule can have this oxygen as sp2, even though when we first learned about hybridization and we were counting up areas of electron density, we would have predicted that this is tetrahedral, right, sp3. But let me show you a drawing. We're going to draw furan on its side, and the best way to do that is this way. And almost messed up again. Oh, okay, not the best drawing. I'm drawing it on its side because what am I going to look at? I think many of you already have guessed. I'm going to look at the p orbitals that are going up and down. And that's why I offset these atoms the way I did, so they don't bump into each other, the p orbitals. So these are all p orbitals. When you look at the pi electrons, we have a double bond between these two carbons on the left. We'll call that these two carbons back here. And a pi bond is made up of 2 electrons. We have a pi bond to the right. Okay, great. Now what about this oxygen? You got to remember, when your atom is sp2 hybridized, don't you have also 3 sp2 orbitals? So I am going to draw for the oxygen, it's sp2. You notice that I'm not drawing the sp2s for the carbons because it's just going to clutter up the drawing. And honestly, all I want to know is, where are the pi electrons? Where are the electrons for the p orbitals? But I need this orbital here because, I'll give it away, one of these lone pairs has to fit there. And you'll see why in just a bit. So I'm not drawing, right, the hydrogens. Because, for instance, this carbon would have 3 sp2 orbitals. One to the carbon, one to this carbon, and then one to the hydrogen. Right, trigonoplanar. You would imagine that there's a hydrogen here, and the geometry is trigonoplanar. Okay. The lone pairs. Oxygen has 6 valence electrons. One of the electrons is here in an sp2 orbital making a bond to this carbon. One of the electrons is here making a bond to this carbon in an sp2 orbital. We have 4 more electrons to take care of, but we only have 2 other orbitals left. So there's going to be a lone pair here, and there's going to be a lone pair here. And it doesn't matter whether you draw the 2 dots in the same lobe. I'm going to separate them, actually. It doesn't matter if they're on the same lobe or not. So what I'm showing here is that one of the lone pairs is in a p orbital. The other lone pair is in an sp2 orbital. Okay, and then let's label that. So while the atom is sp2, maybe I could draw it this way. We could say this is in an sp2 orbital, and this red one is in a p orbital. I know a p orbital has 2 lobes, but I don't want to clutter up this drawing. What I do want to emphasize is that, now those electrons, even the 2 electrons on the oxygen, and only 2 electrons on the oxygen, are being delocalized. Okay, and we have also overlap at the bottom. How many pi electrons do you see now? You count these 2, 1, 2, 3, 4, and you count one of the lone pairs. There are 6 pi electrons. The way that I like to think about this is it's beneficial for oxygen to be sp2 hybridized. Is the molecule consciously choosing for this oxygen to be sp2 hybridized? No. What the molecule is sensing, though, is that it is more stable when the oxygen is sp2 hybridized, and the whole molecule lowers in energy. Okay. If the electrons position themselves so that the oxygen is sp3 hybridized, you lose this sharing of electrons, and the energy of that molecule rises, and well, it's less stable in that I don't even know what to call it, in that hybridization. Okay, so this is sp2 hybridized. Okay. What is your final conclusion? Your final conclusion is that this molecule is aromatic. I forgot what color coding I used, but I'll use green for this video. Aromatic. Okay. It is impossible. Okay, it is impossible to put two lone pairs in that p orbital because remember your rule. You could only fit a maximum of 2 electrons per orbital. Okay, so that is the case for furan. Let me pick out another example. Let's try let's try a nitrogen containing molecule. And um, there's a classic example, but I'm going to save that for another video. Let me think of, how about this? Why not? With practice, this analysis will become automatically, and this analysis will become automatic. You don't have to draw an orbital cartoon to figure out that, oh, if that oxygen is sp2 hybridized, one of the lone pairs is in a p orbital, the other lone pair is in a sp2 orbital. Okay? You won't need to do that once you get a lot of practice in. Ooh, how about this? Okay, we have another potential choice where that atom, do we want it to be sp2 or do we want it to be sp3? Again, question number 1 is it possible or is it possibly aromatic? Okay. All the other atoms are sp2 hybridized. So really the only thing that might be holding us back is what's happening with this nitrogen. So again, we are going to suppose the nitrogen is sp2. sp2. We only have one lone pair. Okay, we only have one lone pair. So instead of drawing the whole molecule, oh, actually, let's do this analysis first. If we suppose the nitrogen is sp2, then yes, rule number 1 is good. All atoms are sp2. Rule number 2, oh, flat. It is a big, oh, very interesting actually. This is disappointing because the way that I have it drawn, and when you make a model of this, these two hydrogens, I think, will be bumping into each other. Not even the hydrogens. This hydrogen right here, let me draw this in a different color. This hydrogen right here, unfortunately, is right on top of that carbon. And there's a hydrogen on this carbon right on top of this carbon. If I force this to be flat, then this molecule cannot exist. We have too many atoms bumping into each other. So, man, unfortunately, we don't even have to worry about whether this atom is sp2 or not. It's already disqualified. See, because of now we don't know what that says. See, that's a hydrogen and a bond. But because of sterics, or you could say bumping, being flat is impossible. Don't worry. I have another nitrogen molecule in mind that's very similar to this. Because now that it's not flat, it can't be aromatic, and it actually can't be anti-aromatic. Remember that anti-aromatic has to fit the first 2 rules, but it becomes anti-aromatic because it doesn't fit the Huckel number. That's the only way that a molecule can be anti-aromatic is you've satisfied the first 2 rules, but rule number 3 is a non-Huckel number. Well, in this case, we already disqualified, so it doesn't matter what's going on with rule 1 and rule 3. We can't be aromatic or anti-aromatic. This conclusion is this is non-aromatic. But I have a fix. That fix is this. This will be good. Ah, what was that fix? The fix was I'm going to make a bond between these 2 carbons. So now those 2 carbons don't have hydrogens, and this can definitely be flat. The other thing that I do want to mention is, I know we have a second ring here. I think this is the first time where we had a molecule that had two rings. I'll say this as plainly as possible. If any part of the molecule is aromatic, you will consider the whole molecule as aromatic. So if for instance this furan here, if there was another ring here, okay, and I ask you, is that molecule aromatic or not? Yes or no? You would say it is aromatic. Or if I ask you which category does it belong in, aromatic, anti-aromatic, or non-aromatic, you will say that this is still aromatic, even if there's a ring that has sp3 carbons, just like we have in this case. Okay, so plainly stated, if any, let's say if any ring is aromatic in a multi-ring molecule, then just say that the molecule as a whole is aromatic. Okay? We haven't yet decided whether this molecule is aromatic or not. I'm giving you this rule because I don't want you to be distracted by this ring here. Okay, I could have easily actually drawn it without that second ring, but I wanted it to be sort of analogous in size to this molecule up here, which was what? Non-aromatic. Non-aromatic, because again, it cannot be flat. Okay, so now let us do our supposing. Suppose this nitrogen is sp2. Okay, let's go through our rules. 1. sp2, check, because I'm only looking at this ring on the right. Okay, sp2, 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 and we're supposing this nitrogen is sp2. Now, if it turns out that this molecule is anti-aromatic, then I would rather this nitrogen be sp3, so we go back to being non-aromatic. Okay. You know what? I know I'm changing this a little bit, but I can actually make it look almost exactly like this by doing this. Right? Now, in this case, all carbons are sp2. sp2, 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 sp2. So I'm going to actually look at the larger ring, the ring that's on this outside. We're going to consider that the ring that I'm analyzing. Flat. Is it flat? We have a 5-membered ring here. Okay, so that is definitely flat. But also, we have a ring here that's sp2 all around. It's almost like a benzene ring, right? A 6-membered ring with all sp2 carbons. We know that that's flat. We're going to assume that it can be flat. And we're going to assume that it actually is flat, actually. Okay, here comes the counting part. How many pi electrons? Again, I'm going to focus on the outer ring, tracing where my pen is going. That ring right there. How many pi electrons do I have? 2, 4, 6, 8. The question is this nitrogen. Is that lone pair in a p orbital or not? I'm not going to draw the whole molecule. I'm just going to draw what nitrogen looks like if it's sp2 hybridized. We have a p orbital, okay? Because I'm really curious where that lone pair is. Now I'm going to draw the sp2 orbitals, something I didn't do with the oxygen furan. sp2. I could do it here because I'm not drawing the other carbon, so it's not as cluttered. sp2. How many valence electrons does nitrogen have? It has 5 valence electrons. We could see that there's a single bond here, a sigma bond. So maybe we have 1 electron from nitrogen overlapping with the 1 electron in the sp2 orbital of this carbon to make that sigma bond. We have a sigma bond down here. So nitrogen will contribute 1 electron to that party, the bonding party, and then the carbon is contributing another electron. We have a sigma bond here to hydrogen, so there's an electron there, and it's overlapping with the s orbital of hydrogen. Okay, I'm not going to draw that. I just don't want to clutter up the drawing. But we have two more electrons to be concerned about, the lone pair. We can't fit two electrons in any of these because they're already participating in bonding, right? And also we can't have three electrons in a orbital. The lone pair is here. For the oxygen, I know I drew it one in each lobe, but let me put a lone pair in just one lobe. Okay. That is part of the pi system because you can imagine that that p orbital is overlapping with this p orbital and this p orbital. My question to you then is, do we count that lone pair? Do we count two electrons as part of the pi electron count? Yeah, for sure. Definitely. Just like we did here for oxygen. So here we have 2, 4, 6, 8, and then these two makes it 10. 10 pi electrons. Is 10 a is 10 pi electrons a Huckel number? Yeah. Huckel is 2, 6, 10, 14, 18, etc. So while this molecule here, where we had some bumping between the hydrogens and the carbons, so the molecule cannot be flat, that is non-aromatic. It doesn't fit rule 2. But by making this a covalent bond between two carbons and we got rid of the hydrogens, this molecule is flat, and also by including that lone pair, it's 10 pi electrons. Okay. Now, we can't just arbitrarily say we include the lone pair just for the purpose of getting up to 6 electrons or for the purpose of getting up to 10 electrons. It has to make sense. There has to be a p orbital there, and the lone pair has to be fitting in that p orbital. So here's the case for nitrogen. Okay, remember how that looks like? And here's the case for oxygen, where one of the lone pairs is in an sp2, the other one is in a p. Okay. So here, it looks kind of strange to them that the p orbital is kind of inward, but this is in a p orbital. It's not in an sp2 because according to our picture, the other sp2 hybrid orbitals are already doing bonding, right? Do you see how this oxygen has no hydrogen here? Right, no hydrogen on the oxygen, so the lone pair there's a lone pair also in the sp2 orbital. Okay. Let me put in one more example, but I'm not going to go over this. This will be part of the practice problems for this video. The example is this. Oh, instead of a carbon there, and instead of an oxygen there, oh man, we have a boron. Actually, I might do this with you. This is very interesting. That boron has 3 valence electrons. It actually has no lone pairs. So we can't make this sp3. There's no choice. This has to be sp2. Just like a carbocation, right? Just like a carbocation has to be sp2. So let me draw that as a reminder. This also has to be sp2. Okay? So that molecule is trigonoplanar. It's flat because it has only 5 atoms. So sp2, check. Flat, yeah, it can't buckle enough to become unflat. So this is in stone. Any 5-membered ring, you're going to consider it flat, move on. How many pi electrons? 1, 2, 3, 4. See, this is not like the nitrogen case where we have a lone pair to kick up from 4 pi electrons to 6. This does not have a lone pair. Boron is, in the periodic table, right? You have a boron, carbon, nitrogen, oxygen, fluorine, and underneath you have, I think, chlorine and bromine. 7 valence electrons, 6, 5, 4, 3 valence electrons for boron. So there is no lone pair on boron. Those 3 valence electrons are participating in bonds. So this only has 4 pi electrons. And I say only because I was hoping it had 6, so it could be aromatic. This is a non-Huckel number. What are we going to conclude here? It satisfies rules 1 and 2, but it doesn't have a Huckel number of pi electrons. You know what? There are very few that we've gone over. This is our third, I think, anti-aromatic molecule. Okay. All right. If you look back in the videos, you'll see 2 other anti-aromatic molecules that you should be on the tip of your tongue. You want to remember those examples. What is an anti-aromatic molecule? The other one was what? Cyclobutadiene, the square. I'll draw it for us. Okay. So those are 2 examples that are anti-aromatic. And the third one from a previous video was, oh yeah, this one. This one, right here. I drew it again here. That's anti-aromatic as well. You could go through your rules, but yeah, this one only has 4 pi electrons and it's flat, and that carbocation has to be sp2. Okay. The examples where you have to choose whether an atom is sp2 or sp3 are the atoms that actually look sp3, right? They have 4 areas of electron density, but have an opportunity to be sp2, so those electrons can participate in aromaticity. Participate, you could even think of it as participate in resonance. Okay? So those are the examples. The ones where the atom is normally sp3, but if you make it sp2, the molecule will become aromatic. All right. I just want to assure you that you're not making these choices every single time. Like we didn't have to choose between sp2 or sp3 for this case. Put it in your notes. Carbocation carbons are always sp2. Put it in your notes. Boron is always sp2. Okay. Now, I do want to go over this unusual molecule, calicine. Calicine comes from the Latin calix, which is part of the word, or makes up the word chalice. You know, a chalice like a cup. So calicine looks like this in one of its forms. I'm drawing this a little bit big. Isn't that a cool looking molecule? Calicine. But the molecule doesn't exist like this in real life. It has a resonance structure. My question is, what resonance structure is the predominant one? Think about it. We are talking about aromaticity. So maybe we should double check if these rings are aromatic or not. Well, this ring up here, the 5-membered ring, yeah, everything's sp2, but in terms of, so this is a little bit tricky because we have this double bond right here. In terms of what pi electrons are really part of this ring system, we're not counting these because these are outside of the ring. So, this doesn't look great. It has 4 pi electrons. Heck, this doesn't look great because, oh, okay, 4 pi electrons up here. What about this molecule here, or this part of the molecule here? That has only 2 pi electrons that are part of the ring. Okay, again, I'm not counting these 2 pi electrons that are part of the, I guess you could think of it as the handle. The question is, can we draw a better resonance structure of this molecule? Take a look at this. What does this ring need? the top ring need to be aromatic? It needs a lone pair, right, to get up to 6 pi electrons. Can you draw me the result if I draw this mechanism arrow? Take those 2 electrons of the pi bond and put it right there on this carbon. There's a reason why I'm putting it on this carbon and not this carbon down here. And I think you'll see once we draw the result. The result, you could pause the video if you want to challenge yourself, okay? Or you could try to beat me. The result is this. Negative charge right there. This carbon, though, lost a bond, so it's positively charged right here. What did we just accomplish? Look at that top ring. That carbon now can be sp2, right? It's the situation where it looks sp3, right? Because it has 4 areas of electron density, but would it benefit it? Would it be beneficial if this was sp2? Yeah, and we saw this before in a previous video where a cyclopentadiene anion was aromatic. If you look back through your videos, in the previous video, we did this charged example right here. So this ring up here is aromatic. Now, look at the bottom ring, right? The bottom ring, all those carbons are sp2. Again, carbocation carbons are always sp2. And we have 2 pi electrons. 2 pi electrons is a Huckel number. You know what? This is also aromatic at the bottom. The thing with this molecule is that in this chalice type molecule, the top ring is electron rich, right? Because we have an anion here. The bottom ring is electron poor, but in both cases they're aromatic. So this is electron rich, and this is electron poor. But you know, electron rich, electron poor doesn't have to deal with aromaticity or not. It's the number of Huckel pi electrons or number of pi electrons. And that you satisfy the other 2 rules, that all the atoms are sp2 of the ring and each individual ring is flat. So this is the major contributor. Now, is this easy? No, it's not easy, because I can imagine, well, what if you're at the exam and you push the electrons in a different way? What if you push the electrons to the bottom ring and instead you have this? That's no good, because look at the top ring. The top ring is anti-aromatic, and we saw that over here. Okay. The bottom ring, I would consider it non-aromatic, because now if that carbon was sp2 hybridized, we would have 4 pi electrons. That's an anti-aromatic Huckel number. So I would rather us read this, as we usually do, as 4 areas of electron density. That carbon right there is sp3. We would make this non-aromatic. And definitely, this is anti-aromatic. 4 pi electrons. Flat, all the atoms are sp2. So do you see how that this resonance structure is much, much, much better than either this resonance structure, right? Because this top ring is not considered aromatic because it only has 4 pi electrons. We're not counting those 2. And this structure is better than this structure because we have an anti-aromatic molecule, anti-aromatic ring at the top. Okay. So that's one of the interesting molecules where, yeah, this molecule is almost fully charged. We have a electron rich and electron poor. And for all intents and purposes, because both the rings are now aromatic, yeah, this ring is negatively charged and this ring is positively charged. and you could still have resonance. See, you can move this charge around by pushing this lone pair here and then pushing this pi bond there. So you could go through all the other resonance structures just from the top ring. Same thing for the bottom ring, right? You know how to move a pi bond towards the plus charge to form a new resonance structure. Okay, so that's an exercise that you could do at home. All right, there'll be more practice problems put in the practice problem set for this video. So again, the best way to be comfortable with aromaticity and identifying aromatic, anti-aromatic, non-aromatic is to do as many examples as you can from the textbook or from your professor. Okay. But at a minimum, for my class, you got to know the examples that we do in each of these videos. Okay. The next video, we're going to do a classic example where we're going to use aromaticity to figure out whether a molecule is basic or not so basic. So we could now rank molecules by basicity depending on whether that molecule is aromatic or not. I don't want to give too much away. You'll see that in the next video.